thank you all for being here today. I'm Leoni Martins. I'm Assistant Clinical Professor of Precision Dairy Nutrition at Penn State, and you may be wondering, what do precision nutrition has to do with soybeans, right? I spend a lot of my time thinking about nutritional strategies to actually deliver nutrients to the cows and make them use those nutrients more efficiently. So that's where the soybean processing ties up with my position. Again, we're going to talk about some of the data I've been generating in the past 10 months, visiting farms across Pennsylvania and trying to understand a little bit better on how these soybeans are fed and processed. Before that, let's just recap the research that is out there with High-Oleic soybeans, so we kind of understand and are on the same page in terms of what to expect when feeding these soybeans based on the scientific literature we have available. Pretty much the first study that looked into High-Oleic soybeans was actually out of Penn State from Alex Christoph lab, where they evaluated High-Oleic soybeans versus extruded soybean meal. So they had the conventional extruded soybean meal, the extruded plenished soybeans, and the whole plenished soybeans. And energy-corrected milk was pretty much the same across those treatments, but they saw a nice response on milk fat content and yield. All right. Apologies for the metric units here, but 1.5 kilograms per day in the conventional soybeans versus 1.6 kilograms per day in the plenished beans. Later on in 2018, data from Wisconsin, Lou Armentano did a comparison of ground plenish and ground conventional, or whole conventional and whole plenish. They were pretty much interested in looking into the particle size aspect of these beans. They didn't have a metric for that particle size other than that these soybeans were ground using a screen at 3/16 inches. So I'm assuming that if we measure these soybeans, they would probably be around 800 microns. All right. No effect of processing on milk production, but then when you compare milk fat, again, feeding the ground soybeans versus the ground plenished beans versus the ground conventional soybeans, you had that nice milk fat response. That makes sense. With less linoleic acid, we have actually more milk fat, so not a big milk fat depression as in the conventional soybeans. And these soybeans were fed at a high inclusion rate of 16 to 18.6%. Adam Locke, back in 2024, did a dose response trial. What I want to highlight here is that they replaced soybean meal and soy hulls with high-oleic acid soybeans. The control diet, or the 0% inclusion high-oleic soybeans, was not balanced for the same fatty acid amount. This is really important for this data because they did see a great increase in energy-corrected milk production, but keep in mind that this 0% diet was not balanced for the same fatty acid level. So energetically, this diet was kind of lower in energy compared with the others. But still, they observe a nice linear response with the higher inclusion rates of high-oleic soybeans, linear and quadratic effects on milk components, so it increased milk fat and also milk protein. These soybeans were processed at 770 microns and roasted at 315 degrees Fahrenheit. And then the last study that I'm going to show and is out there is again from Michigan State. They had a controlled diet that again was low-fat diet, but then they had a roasted high-oleic soybeans, raw high-oleic soybeans, or raw high-oleic soybeans plus a bypass source. In this case was Amino Plus, just trying to make up for the lack of RUP that I'm not getting because I'm not roasting those beans. So can we make up for that? All right. These beans were ground at 760 micron. And they were fed at 16% of the dry matter. And it's quite impressive the response they observed with the roasted beans versus the raw beans. A 7-pound difference here pretty much across the entire study. feeding the amino plus with the raw soybeans was still higher milk production than the raw itself, but not as big as the roasted beans, all right? When I was looking at these data and thinking, what are the current recommendations for processing soybeans? And you go back to the literature and you see that those recommendations date back from late 80s, early 90s. And in theory, we're still using those recommendations because that's what we have. So if you look at that old data with conventional beans, you will see that roasting should be at 290 to up to 315 degrees Fahrenheit with a steeping process of 30 minutes. Then you cool those beans, and those are the estimates of price per ton of this roasting process, all right? Particle size, nowadays we've seen the US soy recommending in multiple resources 750 microns, but I'm going to challenge a little bit this number because I don't think this should be a static recommendation. Probably it's going to depend on what kind of diet you have. So looking at the current recommendations, when they were generated, and you know, the modern cow that we have, these different beans, High-Oleic soybeans that are being fed up to 9, 10, 12 pounds in some diets, are they applicable to our current situation? So what are the metrics that we could actually use to assess that roasting process? What about feeding levels and particle size? So these were questions that I had, and then I submitted a grant proposal to the Pennsylvania Soybean Board with the objective to characterize the particle size, nutritional value, usage strategies, economic benefits, and environmental sustainability of the soybeans. The idea was to visit 15 to 20 collaborator farms to collect the soybeans that they are feeding and actually trying to understand how they are processing and how they are feeding. So in my mind, this was a nice first step to say, all right, where do we need to take research next, all right? First, let's see what's being done in the field, learn with them, and then where are the opportunities to actually improve this process. So the idea is that we visit the farms twice with a 10-week interval so we could measure the within farm variation. Right now we are in the middle of this project, so the data I'm going to show is relative to the first visit. And we conducted a complete feeding assessment trying to understand, all right, what is the implication of these different soybean processing methods on the farm productivity? Can we actually draw some relationships there? So all this data is going to be preliminary work. I hope that by next year we're going to have this completed and the full data published out there. The way I'm presenting this data is High-Oleic soybeans are the yellow plot. The conventional beans are the blue plot. Each of these dots represent one sample. All right, so you can see the dispersion of the samples across the mean. High-Oleic beans were 12 of these 20 samples. Conventional beans were the remaining 8 samples. And the nutrient that I'm going to be discussing will be described on top. And I'm going to also show what is the average and standard deviation for these samples as a whole, combined conventional and High-Oleic. This is something that is like really puzzles me when I collected these beans. I didn't expect such a variation in dry matter, right? So this is the dry matter of the beans ranging from 85 to 98%. So again, thinking about processing and roasting, the temperature applied, if I'm using 300 degrees Fahrenheit to roast a soybean that is 98, can I expect that the roasting procedure will have the same effect as a soybean that has 85% dry matter? Probably not, all right? Protein concentration was less variable, so 38 to 43%. NDF, about 16.5 on average, but again, a big range from 10 to 25% NDF in a dry matter basis. ADF kind of following the same pattern. And then the lignin data, about 1.6% on the dry matter. Not a big range, but going from 0.8 to about 1.8% lignin in the soybeans. This is something that also got me thinking about. Total fatty acids. So overall, 23%. I guess that goes well with the library values. A range from 20 to 27. All right, some will probably consider that a little bit higher than at least I would expect at first. But look at this. Oleic acid concentration as a percent of total fatty acids. Of course, that the conventional soybeans are low in oleic acid, so they are all here less than 20%. But the variation within the oleic acid relative to total fatty acids is kind of impressive, 71 to 87%. And you may ask, why is that happening? I probably need to spend more time with my plant scientist colleagues to actually help me explain what is in the physiology of the plant that, depending maybe on environment, soil, how you handled your crop, will that affect the oleic acid concentration in the soybeans. But again, very interesting, and from a nutritional perspective, it may have an impact if I'm assuming I'm feeding a soybean that is 71% versus 87%, all right? Roasting temperature, going from 260 degrees Fahrenheit to up to 304, on average 281 degrees. Roasting duration, pretty much all samples roasting from 1 to 2 minutes. I have one outlier here that reported as 37 minutes. Maybe that's not true, but that's the data I collected from the farm. So to me, he probably misinterpreted that information. But most farms, the transit time for the soybeans to go through the roaster is about 1 to 2 minutes. A lot of farms using these mobile roasters. So actually 15 out of these 20 samples I'm showing data on were done with these mobile roasters. For you that don't know what that is, it's a roaster that will come to your farm. The beans will go in the roaster and will exit the roaster after 1 to 2 minutes. And here you can measure the temperature of the beans. And then the farm has the option to use this steeping cooling bean, which I would frame this as a controlled steeping and cooling. It's not quite the steeping process that you have in a processor that has a stationary roaster, but at least you know that those beans are steeping for a few minutes and cooling down, so you can store them right away. Again, after steeping those beans and cooling those beans, they will go into the storage bin. And what I would like to highlight here is that all these samples that are clustered on the 0 line are the farms that did not use this controlled steeping and cooling. That doesn't mean that the beans, when they exited the roaster, that they cooled down immediately. Actually, some of these samples, they took 12 hours to cool down. But it's just that I could not control, or the farm could not control, the steeping and the cooling process. All the other samples could be controlled, all right? Mean particle size, huge range. Of course, that the 4,500, these 3 samples here on top, or 5 samples considering the conventional, are the whole soybeans. Nobody's feeding whole soybeans, but when I went to the farm, I could not get the ground soybeans because they were grinding immediately before mixing it with other feed ingredients, so I could not separate the soybeans. But the highest particle size we saw were soybeans cracked in halves, and they are about 3,500 microns. But again, going from 450 to up to 4,500, let's see, 450 to up 3,200. This is the standard deviation of these particle sizes. Again, pretty big range. What I observed in this limited data set I've seen is that the rolled beans seem to be more consistent in terms of particle size compared with a hammer mill. And that makes sense when you start considering number of hammers, how the condition of these hammer mills is, or how is maintenance going on with those hammers, RPM. So there's a series of factors that will kind of change actually the way that these soybeans are processed. Some protein metrics to help us understand the roasting process. I'm not sure if there is anybody using ADICP as a metric or ADIN. I have these values here going from 0.7 or 0.5 to 1.2. Can be quite variable, and the ICP the same. On average, we have 0.77 as a percent of dry matter and 5.9 for in the ICP. PDIs, if you go out there and try to find resources on which numbers to use, PDIs will be pretty much 9 to 11. That's the recommendation you can find. Most of our samples fell within that range. We had a few below, a few up. Urease activity, majority of our samples was below that range, we'll discuss more about what's the implication of the PDI on how to evaluate the soybeans. We submitted these samples for the Ross MSPE analysis. We did this with Cumberland Valley, and these are the results we got back from them. So soluble crude protein, average 4.6, but look at the range. 3 and 5 up to 6%, all right, almost double soluble proteins. RDP, average 30.5, and that's where I started scratching my head. If RDP is 30.5, a range of 10 to 55, it means that RUP is about 70%. Look at the two pools of samples that we had here, especially with the High-Oleic. So we had a group of samples at about 60%. That's probably the value I would assume, or I would like to, I've been trained to assume that we're going to see after roasting the beans. But we have a pool of samples that is about 80% RUP. If that's true, that cow is not digesting that RUP, maybe, unless I'm grinding it to 400 microns and then I'm making that available, right? Intestinal digestibility, 75 to 95%. Total tract undigestible crude protein, 5 to 15. There's one sample here about 18%. So what do these values tell us? Can I trust these RUP values? I was thinking about this and went to their challenge in Ohio a few weeks ago, and I happened to meet Mike Van Embert there, and I asked, is Ross assay overestimating RUP? And then he grabbed a piece of paper and said, let's talk about this. And what he said is, the assay was never meant to measure RUP, but undigestible nutrient. You could derive RUP from that assay if you do the modeling on the KD, all right? So just as for an in situ incubation, you could use the data to model the fractions A, B, and C, and then calculate RDP and RUP using those traditional equations we have. What the labs are reporting is pretty much a 16-hour residue. So this is not the same as modeling these fractions. Maybe for some samples you will, by chance, come to close values, but maybe it's going to happen what we saw, different distributions with RUPs going up to 80, 85%. We did the in situ incubations in our lab. We just finished these incubations probably 2 or 3 weeks ago. I unfortunately do not have the protein data. We have over 700 bags, so my students need to work way harder to get this done. But if we use dry matter degradation as a proxy to what is disappearing in the rumen, this is our 0-hour in situ dry matter disappearance, and this is the KD that we could calculate based on those samples. So on average, 1.3% per hour, that's the degradation rate in this data set. If we assume a 16-hour retention time or for these soybeans, we could calculate how much is disappearing, how much is passing to the intestine. We come down to that 54 55%, which to me makes more sense than the average of 70% RUP, all right? But again, look at the range. It's a pretty substantial range, all right? How does roasting temperature explain these protein metrics? It doesn't, at least in our data set. So roasting temperature had absolutely no relationship with any of these variables except for the ADICP. R square, 0.35, 34%. That is the determination coefficient. What about steeping? Remember, steeping here is not the same as the industry. It may be the controlled versus uncontrolled steeping. Then it starts explaining way more variables. And what I'm going to highlight is the total tracked undigestible crude protein. So all these farms here clustered in the 0 line are the farms that are not controlling the steeping process. All the other farms are controlling the steeping and cooling. As they do more steeping or controlled steeping, we have less of the undigestible total tracked protein, meaning that we'll probably extract the most out of these beans when we feed to the cows, all right? How does ADICP urease activity relate to the in situ degradation? Pretty much they don't, at least again in this data set. What about PDI and the ROS RUP? Again, very low correlation across these methods. And I just want to make the point is that PDIs, we always see people saying they don't work, but that has been acknowledged back in 1995 by whoever put this paper out there, that they are good metric to identify a sample that is raw versus a sample that was roasted. But I cannot make a point on what is the difference across these samples after a certain temperature, all right? Particle size, how does that influence or is associated with the PDI, ROS, MSPE, or the 16-hour undigestible dry matter? Again, common sense, these are in vitro or kind of in vitro assays. When I put in the cow, of course, the coarser the particle, the highest undigestible dry matter or protein I'm going to have in the rumen. So to me, this makes more sense because I'm feeding cows that way, not that way, all right? Need to keep that in mind. So really quick, there's substantial variability. You saw that. Because nutrient can vary with environmental conditions, maturity and storage, I think you should be testing more frequently these beans. We don't have enough evidence for particle size recommendation. I think 750 microns may be adequate for most diets, but if now I'm feeding high starch levels and high moisture corn, I may be challenging the cows to some extent. And we need more evidence to validate some of these methods that I can actually get the lab analysis and say, well, this is the number I'm going to use in my nutritional formulation software. What I would do is get the 16-hour in vitro digestibility and use it as a metric to change tracks over time. So if things start going up or going down, I will calibrate myself on what I need to do in the term of diet formulation. Path forward, again, we need to evaluate these interactions. And really quick, just acknowledge the collaborator farms and their nutritionists for letting us come to the farm and collect these samples, really trying to generate data that they may use and improve their work on a daily basis.